Now let's look at one last thing. And that last thing is the limitation on the value of Kp. And that's the constant that we apply to the message in phase modulation. So in frequency modulation, we could have that constant Kf be anything. But for phase modulation, we should restrict the value of the constant Kp from minus pi to pi. Let's see why that's important. Let's do that by considering two messages with two different values of Kp. So the two different messages look almost the same. The first message in blue is the one that we just studied, and that's a message that goes from 1 to -1. And it has a Kp value of pi halves, which is within the original specification that we wanted. But the second message is red. That message goes from positive 1/3 to minus 1/3 every 0.5 seconds. And this one has a constant Kp of 3 pi over 2. Let's see why this is not a good idea to have the red message with the constant that's larger than pi. So for the blue signal, we can see that if we substitute in our value for the carrier frequency and for the message, we'll get a phase modulated signal of sine 2 pi times 10t. But what about the red message? Well, for the red message, we're actually going to get the same thing because the value of Kp is 3 pi over 2, and the message is 1/3. When we substitute this in, we actually have the same phase modulated signal, which is sine 2 pi times 10t. Now, why isn't this a good thing? Well, if we have two different messages and they've been modulated and we get a phase modulated signal, and the phase modulated signal is identical, that means that if we had a receiver, it would not be able to distinguish between the blue message, which has the phase modulated signal of sine 2 pi 10, or the red message, which has a lower value, but also has the same phase modulated signal of sine 2 pi 10. If we look at all the different graphs that we looked at before, we can see that the message between red and blue is slightly different. The derivatives are almost the same. The red derivative has impulses that are slightly smaller than the blue signal, but the instantaneous frequency is going to be identical because the Kp value, the constant value multiplied by the derivative, is going to be the same. And then the angle is also going to be the same throughout because that's the carrier frequency multiplied by time. That part's the same. And then, like we looked at before, the constant Kp multiplied by the message is going to give us the same value. So the angle of the phase modulated signal is the same for both messages. And at the very bottom, we can see that for all time, the phase modulated signal between message 1 and message 2 is going to look identical. And if the phase modulated signal looks identical, that means that the receiver won't be able to distinguish between message 1 in blue and message 2 in red. So because of that, we should always try to restrict the value of Kp between minus pi and pi. If the value is not restricted from minus pi to pi, then a digital message may not be able to be recovered uniquely. One other thing that you could do to avoid this problem is you could just avoid messages that have jump discontinuities like the one we saw. So if you had a message that doesn't have those jump discontinuities, you would not have to restrict your value of Kp. This is also the same as saying that we should try to have messages that are continuous.